you have a good break? I was sick most of the break. Yeah. Remember I was sick? Oh yeah. You know that day that I didn't tell y'all class was canceled? I woke up, I must have been delirious, I thought I was quiet. So I canceled one class, and then I woke up, got out of bed a little after 2, and I was getting texts and emails, and I was like, oh my God, it's Wednesday. It happened. So we're a bit behind. I'm very behind. I meant to get caught up with the break, and of course I didn't. So I was sick. Now I think I have allergies at this point. I still feel a little down. I looked online today, and I was like, hey, what did I put on D2L for y'all so far? And I realized I put nothing on there for y'all so far. So that's what I got to do to get caught up. I intend to do the same way in test 2 as I did test 1, have everything there that you can practice. So I've got to get caught up on that. I'm going to push the test out at least until next Wednesday, possibly the following Monday, just so we can get caught up. I want those questions up there for y'all long enough for y'all to practice them and for us to review them. I am going to lecture on some new topics today, and then I'm going to go back and review what I didn't put on test 1 was molarity and dilution, concentration type stuff. So I'll go back and review that, and there's a couple other things I want to do in this chapter. We spent most of our time on, in chapter 4 and chapter 4.2, the redox reactions. I'm going to do these reaction stoichiometry, reaction rates, reaction yields, quantitative chemical analysis. Some of that, and I expect will be thermochemistry too. We can get through that before test 2. So I think we'll be in good shape for what we've got to finish. Let me just, and I will between now and Wednesday start getting stuff on there. But for now, I want to start here. I'm going to go back to, I've had a couple of questions that were on test 1. I skipped up to this chapter and did a couple of things in test 1. A couple things from this chapter in test 1. But let me remind you these. This was on test 1. So understanding how many moles is important for what I'm about to do. How many moles of O2 are needed? Reduce 5.94 moles of CO2. That was the question, and I give you the balanced reaction. And that was one of the questions. So just as a review, the way you do this is how many moles of O2, notice I said moles, to produce this many moles of CO2. When it's all moles and grams aren't mentioned, you don't need the grams per mole of anything that's here. So all we really need here is to relate O2 to CO2. So I'll start with this. 5.94 moles of CO2. Over 1. Moles of CO2 is on the top here, so I need it on the bottom here. But what's going here is the molar ratio in this reaction. CO2 to O2. We're asked for moles of O2. So we're going to take 4 moles for CO2, 7 moles for O2. Moles of CO2 cancel, moles of CO2 cancel. Will end in moles of O2. And if you just calculate that out, it's 5.94 times 7 divided by 4. Get a number. This must come out to 19.4, I think. No. Should be about. I guess I got to calculate it. This wasn't one of the bad questions on test one, was it? $702,602. So just to remind you how to do that one. And now I'll do one where grams is mentioned. Notice this one's very simple. You only needed this, and then this is information you were given. This part right here is literally this. And then the only thing you needed to get was the molar ratio for these two things. These two things. Okay. So let me do one that where grams are needed. And then I'll show you something new. So I did skip up to this chapter just to cover the basics of reaction stoichiometry, quantitative reactions. Now, this one is how generated when 12.6 grams, 12.6 grams AgNO3, and then I gave you this. So you're getting all of that. And notice this says how many grams, and it also says 12.6 grams is the G per gram. That's what tells you need the grams per mole of the things involved. So you need the grams per mole. It says grams of AgNO3, so you need the grams per mole of AgNO3. And then asks for grams of BaNO3 too. So you're going to need the grams per mole of BaNO3 too. But I gave you those in here, so we won't calculate them. But the AgNO3, that one I gave you as grams per mole. I gave you for the BaNO3 too. So you don't have to calculate it yourself. And of course, I tell you to take these and go for this one, for AgNO3, it's the grams per mole means grams of AgNO3 is 1 mole of AgNO3. So this is the more formal way to write that. And the more formal way to write this, 261.34 grams one mole. And that's the way we use it in the equation. So since grams of BaNO3 was mentioned, I'm going to need grams per mole with that. And then grams of AgNO3 is mentioned, so I'm going to need that. And we're still going to need the molar ratio between these two. So you start with what you're given, 12.6 grams. AgNO3. I've got grams of AgNO3, so I need grams of AgNO3 down here. This is where we're going to use the grams per mole for AgNO3. I've got grams on bottom, so the 169 goes down here. And the 1 mole of AgNO3 goes here. So I've literally used this, but I've used it flipped over. Because this said grams of AgNO3, so I need grams down here. The next thing is the molar ratio. But you can still use this as your guide. Look up top, I've got moles of AgNO3, moles of AgNO3. And the other thing we're talking about is BaNO3, so moles BA. And this ratio is the moles of AgNO3, there's 2 of those. Moles of BaNO3, there's 1 of those. So there's the molar ratio. And then the last thing that's going to go here is this. I've got moles of BaNO3 moles of BaNO3, so that goes here. And now we're using this, 1 mole of BaNO3 to 261. So before we only needed this because we were going moles to moles. Now we're going grams to grams, so we need the grams of this, grams per mole of this, grams per mole of this. That calculation will give the answer to this. Mark the correct answers on here. So 12.6 times 261.34 divided by 169.87 divided by 2. So 9.69. That will come out. 9.69 grams of BaNO3. So that was the answer on the test. So this sort of quantitative analysis is where we're headed. Those of you who took chemistry before, do you remember limiting reactant? Limiting and excessive. Maybe they don't always do that in high school chemistry. Let's see, limiting and excess. There's more than one way to do this. I have my way of doing it that I think is easier. Okay, so the subject here is so when we do these reactions, you can put however much of each reactant in there you want. There's only a certain combination of them that's going to complete the reaction. But, well, let me do it like this. If I have this reaction, 3 silicon, it's a solid, plus 2 nitrogens, that's a gas, 2 and 2 fluids. Three of those, 2 of those, okay. So let's say you're given that. This is example 4.12. Chapter. All right, and you're told you have 2 grams SI solid. And I told you to have 1.5. Just to get the significant figures right. 2.00 grams of this, the silicon. We have 1.50 grams of N2. But before I solve that, let me say, if you think of these in moles, so forget what I have in the box here. If I need 3 silicons, 3 Si, and 2 N2s, so 2 N2s, I have N4. If that's what I need, but let's say I actually put into the reaction mixture 2 Si's and 2 N2s. I can't really make that because I don't have enough of this. I need 3 of these, not just 2 of them, if I'm going to make this. So I really can't do this. I have to put enough of this in there to react with everything here to actually get the reaction. You see what I'm saying? All right, and let me say, what if I put into the reaction, so multiply everything by 2. 4, 2. So if I put 6 moles of silicon and 4 moles of N2 into a reaction mixture, I will get 2 Si3N4s. So this is balanced, and this is balanced. This is not balanced. 3, 3. No, we leave that like this. So this is balanced, and this is balanced. So both of these would go. If this one reacts, there's nothing left over of silicon or nitrogen, and we form all silicon nitride over here. If I do this, all of the silicon and all the nitrogen reacts, and I get this much silicon nitride. You with me? It's not that complicated. I'm making it seem more complicated than it is. But what if I put 5 moles of silicon in here and 4 moles of N2? How much of this am I going to get? Well, what I've got written here, if I did it like this, I'm going to get Si3 and N4 out of that, Si3 and N4 out of that. That's how I get 2 N4. Do you see that? I'm depicting this in sort of a pictorial way. I've got 6 of those, and I've got 4 of those. 6 of these, 4 of those. Therefore, I can make 2 of those. I can make 2 of these. If I'm going to follow what I'm doing here. That. See what I'm saying? But if I only had 5 SIs, well, I can make 1 of these, so I can make some of it. But what's left over is I make this, and then I have Si, N2 left over. These reactants couldn't finish reacting because they didn't have they needed 1 more Si to make the molecule. So this is what will be left over in the reaction mixture if I mix it this way. You see what I'm saying? You see what I'm saying? So I can make a reaction mixture like this. The only problem is I've wasted some of my reactants. I've wasted some Si and some N2 that didn't become Si3N4. All right. I had exactly enough N2 to make this reaction work. What I didn't have enough of is my Si. So what I'm trying to show you here is this is the limiting reactant, the Si. There wasn't enough of it. And in some sense, you can think of the N2 as an excess because there's more of it than was needed for this. But there wasn't enough of this needed. I needed 3 of these to go with these 2. So that's the idea of a limiting reactant. When you mix things together, if you don't mix them in the perfect stoichiometric amount, you're going to have some reactant left over. All right. Limiting versus excess. So I did this in moles. In this problem, we're given grams, and that just makes it a little more complicated. But here's what you do to figure out which one is limiting and which one is excess. All right, you pick one of the 2 reactants. You just pick one. I usually just pick the first one there when I explain this to people. I'm going to pick this one. And I'm going to go, okay, I've got of Si. Now I need the grams per mole of Si. So this is how you figure out which one is limiting and which one is excess. So I got that from here. Grams per mole, so grams of Si. 1 mole of S silicon is 28.09. So I got that from the periodic table. It's moles of Si. I'm going to do the reaction ratio of these 2 to each other. So I've got 3 Si to 2 N2, 3 moles of Si to 2 moles of N2. And then next, I'm going to need the grams per mole of N2, moles of N2, moles of N2. I need moles of N2 on the bottom. Nitrogen is 14.01, so N2 is going to be 28.02 grams of N2. And notice it is set up very similar to the last review problem I did. You're given grams of things, so you know you need grams per mole. The grams per mole of silicon, straight out of the periodic table, is this, grams per mole. Here's the molar ratio. 3 of these to 2 of these, 3 of these to 2 of these, from the balanced equation. And then I needed the grams per mole of the other thing. So it looks very similar. It's set up almost exactly the same. And let's see what we get. 2.00 times 2 times 28.02 divided by 28.09 divided by 3, and we get you with me on this calculation? How you set it up? You guys okay? I know it's tedious and I haven't given you the punchline yet. All right. At this point, remember I just chose to go with Si, silicon. I don't know why I'm not saying silicon. I chose to go with silicon, so I'll put that here. And then I built my equation across ending with N2. So here's the thing. I'm going to write the word need down here. I need 1.33 grams of N2 if I've got this much silicon. But here, I have go back to the beginning of the problem tells you you have 2 grams of silicon, which is why I put 2.00 here. And the problem tells you you have 1.5 grams of N2. This is how much I actually have. This is how much I need. Do I have as much as I need? Yeah, I have more than I need. That means this is excess. I have more of it than I need. So that was excess, which necessarily makes this one the limit. So that trick at the end, this is how much I need, this is how much I have of the N2. That tells you whether the N2 is excess or not. We might have found the opposite. We might have found that we have less than we need, and that would make that one limiting and the other one excess. You with me? Okay. Remember at the beginning of the problem, I said, just pick one. And I decided to go with silicon. But let me say again, I found this was the excess, and this one was limiting. But what if I had chosen the other one? So let me go the other direction and say, no, I'm going to choose N2 for this. So then I would start with 1.50 grams of N2. Next, I need the grams per mole of N2, which it turns out is 28.02 here. Next is the molar ratio, but it's going to be flipped over. Moles of N2 on the bottom, 2 moles of N2, 3 moles of silicon. Now I need moles of silicon on the bottom. Moles of silicon. And that's this. So 1 mole of silicon is 28.09. And let's see what we get. 1.50 times 3 times 28.09 divided by 28.02 divided by 2. And I'm going to write need here. I need 2.26 grams of silicon, if that's how much N2 I have. This is how much silicon I actually have. So I need 2.26, but I only have 2.00. This is how much I need. I have 2.00. That's how much I have. I need 2.26. So do I have enough? Do I have enough? If that's how much I need, do I have enough? No, I don't. That tells you that's the limiting one, and the other one is excess. But that's what I already determined. I already figured out that was true. So what I'm saying is you only have to do one or the other. You're going to come to the same conclusion as long as you do the math. See what I'm saying? Here, I have 1.50. I only needed 1.33. So this one was excess, which meant the other one was limiting. Down here, I did it the other way, and I said I need 2.26 of silicon. I have only 2, so that one's limiting, and the other one's excess. I come to the same conclusion no matter which one I decided to use. So you just pick one of the reactants. You go through the calculation. You write need above your calculation. Write have next to what the problem gives you, and you can determine whether you have more than you needed, which means excess, or less than you needed, which means limiting. You follow that? That's how you decide which one is limiting. The reason when you want to figure out which one is limiting, because if you're going to predict how much product is made, you have to use the limiting one to calculate the product. In this case, if I wanted to know how much Si3N4 I get at the end of this, how many grams of it, I can figure that out, but I'm going to use this one as my starting point. Let me erase this. So there I was relating one reactant to another reactant. Now that I found out which one is limiting, I'm going to use that reactant to relate to the product, which means in the middle when I get this molar ratio, I'm going to relate silicon to this rather than N2. So let's start by going, I'm given 2 grams of silicon, limiting. I need the grams per mole of silicon, which I have over here. So grams silicon to 1 mole of silicon. The grams are 28.09. 28.09 grams of silicon. Now this molar ratio I'm going to use is between the silicon and the Si3N4. Moles of silicon here, so I need moles of silicon there, and up here, now I'm going to use moles of Si3N4. And what's the ratio here? 3 silicons to 1 of those silicon nitride. Okay, and then that gives me moles of Si3N4, so down here we can cancel. Now I need the grams per mole of this. So I gotta know there's three of those, and there's 4 of those. Off the periodic table, 14.01. Silicon is 28.01. Times 28.09. Times 14.01. grams. 84.27 plus 56.04. 143. Okay, so I found that. So now I can fill this in. 1 mole of that. 140.31. 2.00 times 140.31 divided by 28.09 divided by 3. That's how many grams of this product I will get if I mix the 2 reactants in these amounts. We had to first find out which one was limiting, and then we used the limiting one to find out how much product we got. That's the whole point of finding out which one was limiting. I know it's a long walk, but do you see what we're doing? All right. I want to add something here, a vocabulary word. Now, what we just calculated is called the theoretical yield. Yield is a word we use to refer to the products, as in how much product did we get? What did this reaction yield? Theoretically, if you mix these 2 things together in these amounts, theoretically, you should get 3.33 grams of your product. And I specified that it's theoretical because in practice, typically you don't get as much as you expect. You lose a little bit through a filter somewhere, something doesn't go quite right, so you usually get a little bit less than you expect to. You might have a little bit more once you weigh it, but that's because there might be contaminants in it or it's still wet with whatever solvent you use. But the better way to put it is almost always your yield isn't always as perfect as it theoretically should be, which leads us into the next topic, the percent yield. So I would call that the theoretical yield that we just spent all that time trying to figure out. First, we had to figure out which one was excess and which one was limiting, and then we used the limiting one to relate to the product, and then once we figured out how much product that meant, we call that the theoretical yield. You with me? I know it's a long walk. That's your limiting reactant versus excess reactant. Example 4.12 didn't go as far as this. It just said figure out which one is limiting and which one is excess. I went ahead and finished it out because that's the next step. There's another example. Check your learning. I won't calculate the theoretical yield here, but let's see if we can figure out the limiting versus excess for another one. I'll give you the equation. They don't quite tell you the whole equation, but H2, O2 makes H2O. Guess I have to balance it. So I'll give you the balanced equation that balances it. So it gives me 4 hydrogens, that gives me 4 hydrogens. 2 oxygens, 2 oxygens. Okay, so there's the balanced equation. And you're told, part of what you're given, 5.00 grams of this. Oxygen, you have 10.0 grams. So the question is, which one is the limiting reactant? So that's the information you're given. What's your first step? Say again? Yes. Well, once you find the limiting, you know the other one is excess. So let's just say find the limiting reactant because that's the one we really care about. But what's your first step in doing so? Pick one. That's your first step. Just pick one. One of the 2 reactants, whichever one you care to start with. I usually just pick the first one. So we're going to start here with H2. 5 grams of H2. If you remember that your first step is just pick one, it'll get you rolling, so you're not sitting there confused. So we're going to need the grams per mole of H2. So what are the grams in 1 mole of H2? Well, there's 2 hydrogens, and hydrogen is 1.01, so it's 2.02 without bothering to do it more formally. On the periodic table, it's 1.01, so it's 2.02 if there's 2 of them. 2 of them. All right, and then we need the reaction ratio between the 2 reactants. Moles of H2 goes on the bottom. And then moles of O2 goes on the top. There's 2 moles of that to 1 mole of that. You see where I'm getting those numbers? 2 moles of H2 to 1 mole of O2. Now we need the grams per mole for O2. Mole of of O2 goes on the bottom, moles of O2, moles of O2. Grams of O2. Oxygen is 16.00 on the periodic table, so it's 32 grams of O2. So that's our full equation. So let's see what we get. 5 times 32.00 divided by 2.02 divided by 2. Yeah, it's 3 significant figures. That's exact, that's exact, 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 exact. 4 significant figures, 3 and 3 is 73, 39.6 grams of O2. Before I leave this little area, I'm going to write the word need here. I need this many grams of O2. I have, how many grams of O2 do I have? 10. This is what I was given. This is what I need, but this is what I have. So is O2 the excess or the limit? I need this much, but I need 39.6, but I only have 10. That's the limiting reactant. O2 is the limiting reactant, which necessarily makes the other one excess.
A quick question for the limiting reactant. Can you just look at which one has the lowest number of atoms in the equation?
No. This balanced equation doesn't necessarily mean somebody mixed it in this perfect amount. What they did is put 5 of this and 10 of this. And that wasn't a 2-to-1 ratio.
Yeah.
Once you broke it down into numbers, it wasn't. There is more than one way to do this. I think my way is the best, but if you think you can see into it and it works for you, it's fine. But you're going to have to involve the grams per mole. You're going to have to involve the molar ratio, just if you think of another way to do it. But you can figure out which one is limiting with one shot if you follow the way I'm telling you to do it. If it's moles, you might be able to figure it out, but you still have a molar ratio. I mean, if you had something where it's 1 to 1, like if I was doing there is such thing as H2O2, that's peroxide. It's 1 to 1 to 1, and I said I had 2 moles of this and 1 mole of this, then yeah, I guess you could go, okay, yeah, that's limiting for sure. But what complicates it is you have a ratio of these two, and then you're given grams, you have the grams per mole to deal with. My brain doesn't look through all that. I would always just go ahead and calculate. As many years as I've been doing this, I can't just see into it. Unless it's 1 to 1 ratio and you're given moles, that's the only case I think I can do it. But most of these types of problems, for sure on the test, I won't make it that simple. I'll make it where you have to calculate it. Make sense? All right. So if we wanted to go to the next step and go, what is the theoretical yield of H2O if I mixed it this way? We could figure it out. But we know that we're going to use the ratio of O2 to H2O, not the ratio of H2 to H2O. But I'll just leave it there. Okay. Limiting reactant. Again, limiting reactant is important because you don't always, when we make a reaction, we almost always make one of them excess, just to be sure that we're getting the analytical amount. So it's pretty typical to do it with one of them excess and one of them limiting. Okay, that's limiting reactant, excess reactant. Let's do. Percent yield. If every time you did a reaction, and you always got exactly how much you theoretically needed, then you would always have 100% recovery, 100% yield, and all of this excess limiting stuff wouldn't matter. Since it doesn't work out like that, we talk about percent yield. And let me give you, let me put it like this, percent yield. I think it helps to say this. That's very simple to calculate. That's easy. Figuring out what the actual yield is easy, and I'll say dot, dot, dot. It's pretty much always given in one of these types of problems. And then there's one more thing. That's the hard part. So percent yield is a simple idea. Actual yield is actually kind of even more simple. Theoretical yield, as I've already shown you before I did this problem, it's a long walk to find the theoretical yield. You got to find the limiting reactant, and then you got to go back to the beginning and figure out what the yield is, theoretical yield for the product. So this concept of the percent yield, just realize percent yield, actual yield, that's the easy part. It's a theoretical yield, that's the kind of the long walk. So let me show you what percent yield and actual yield is. This is 30. Here's a reaction. Zinc gives you Cu plus zinc sulfate. This one is kind of simple because it's all a 1-to-1 ratio, but we're dealing in grams, so we can't just think simple about it. Copper sulfate, 1.274. That's how many grams of copper sulfate is put into the reaction. 392. Okay, in this one, they save us a little trouble. They tell us this is excess. So the information I've sort of diagrammed up there is the information that's given. They give you the reaction, they tell you this much copper sulfate was put in, and they go ahead and tell you this was in excess, and this is how much copper was recovered as a product. And then what is the percent yield? Percent yield. All right. Because they told us this is excess, we know this one is limiting. All right, LIM up here. Okay, the percent yield, like I said, percent yield is simple. It's So like I said, the percent yield is pretty simple. There's an actual yield, like I said, and that's very simple to know what that is. Theoretical, that's a long walk. But it's actual divided by theoretical times 100, and you end up with a percent for your yield. That's the equation for percent yield. And they have told us, upon reaction of 1.274 grams of copper sulfate with excess zinc, 0.392 grams of copper metal was obtained. This is why actual yield is so easy. They just told us what the actual yield is. 0.392 is the actual yield. And that's why that's so simple. You have to be told. There's really no way to know. The actual yield you get from a reaction really depends on how you did the reaction, your technique. Did you do it in a flask? Did you have the right filter? Were you really careful when you filtered it? Did you not lose any when you dried it out? All that type of stuff. There's no way for you to calculate that. It comes down to like procedural error or human error. So the point is, you have to be told this. If someone's making up a problem for you to solve, they have to tell you that. There's no way you can calculate that. It's just a totally made up number. See what I mean? Anyway, actual yield is generally given. If you're not given actual yield, then you're given the theoretical yield, and you're given the percent yield, and you're just using this to find out what the actual yield was. But typically in these problems, you're given the actual yield, what actually happened in the lab when this was done, with all the imperfections that go into doing lab work. So what we really need to do, since we're given actual yield, and we're asked to find percent yield, we've got to find the theoretical yield. Then we can calculate the actual yield. And they've made it easy for us, at least they've taken half the work out of it. They told us which one is limiting. So we can just use this and relate it to copper, and then we can solve for it. Copper sulfate, did they give it to us? No. Well, I'm looking at the solution on here. Copper, I'll go this far. There's four oxygens, there's one silicon, one sulfur, and one copper. If you go up through all that, you're going to find 159.62 grams per mole for copper sulfate. So I'm just going to kind of skip that. That's just to remind you what I'm doing. 159.62 grams per mole. So like I said, we're going to use the limiting one. So we're going to go 1.274 grams of CuSO4. And then we're going to use the grams per mole here. Grams are going to go on bottom. CuSO4 to 1 mole. And the grams are 159.62. Next is the molar ratio. It happens to be 1 to 1. On a test, I always try to not let it be 1 to 1, just so you have something to sink your teeth into. But in this case, this is balanced. So it's one of these to one of these. I need moles of CuSO4 on the bottom to 1 mole of Cu. It is balanced, right? Yeah, it's balanced. All right. So you've given us Cu in grams. So I've got to get grams here, so I need moles of Cu on the bottom. 1 mole of copper is, I don't have it memorized, 63.55. That's going to give us our theoretical yield. Once I calculate. This is the actual yield. That'll be the theoretical yield. Then we can calculate the percent. You see? .274 times 63.55 divided by 159.62, and that's it. Exact. 4 significant figures, 5, 4. So I guess I've got to keep 4 of these. 5072. Theoretically, I should get 0.5072 grams.
grams of CU. So to calculate the percent yield, I'll put the actual 0.392 over theoretical times 100%, and that's going to be the percent yield. No, I forgot to multiply by 100. 77.287, which is 0.29. That's right, 77.29. I bet they forgot. Oh, 3 significant figures, 4. So I need to round this to 7.3. There you go, percent yield. 0.392, that's the
actual divided by,
yeah, actual, and this was what we calculated for a theoretical. It's not hot in here, but it's humid, isn't it? I've been in here since noon, and I've messed with that dehumidifier, and it's still not really doing its job. I guess we'll do the check your learning for this one. Yeah, they tell us which one is excess here too. So it saves a little trouble. So this time we're given CCl4, carbon tetrachloride plus 2 hydrogen fluoride. Ratio is going to be 1 to 1 again here. We get 12.5 grams of that, our product. 32.9 grams of CCl4 is put in it, and they tell us that this is excess. So we know that this one is limiting. So what do we call this? Huh? Actual yield. Just to give it a what we have to spend all our time doing is figuring out the theoretical yield. And then we can figure out the percent yield very easily. Four of those, one of those. On the periodic table. also going to need one of those, two of those, two of those. Oh, it's flying. Double checking my work here. 38, okay. 12.01 plus 70.90 plus 38.00. That's stuff we're going to need. All right, we'll start with the reactant. Grams of CCl4 on the bottom, moles on top. Grams of CCl4 is moles of CCl4 on the bottom. Moles of, that's freon. CF2Cl2. And this happens to be 1:1. And is balanced, right? You got 2 H's, 2 H's, 2 40s. All right, but it's not always 1:1. And then moles of freon down here. Grams. This one is 120. All right, so that's our radical yield. 32.9 times 120.91 divided by 153.81. That's it. And we're in 3 significant figures here. That's what I got, 25.9. So this is theoretically what we should get, 25 and change. We only get 12 though in actuality. Actual yield, 12.5. The grams cancel. The grams of CF2Cl2 cancel because it's grams of that either way. So I'll just drop them off. That's our theoretical yield. It's less than half. Follow that. That humidity's getting me. All right. I'm going to do end of chapter exercise 71. It says outline the steps to determine the limiting reactant. And then down at the bottom says, now determine the limiting reactant. I'm not going to outline the steps, I'm just going to perform them. 2 chromiums, 2 phosphoric acids, 2 Let's determine the limiting reactant. Here's our 2 reactants. In this case, we're given moles. Instead of grams. And it is essentially 1-to-1. So I think you can just tell which one is limiting and which one is excess. Can you tell which one is limiting and which one is excess? I'll do it more formally, but I can see which one is excess. It's kind of what he was asking before. This is essentially 1-to-1. It's 2-to-2, but that's 1-to-1. So I think that has to be excess. But if you want to do it formally by moles, if you just pick one, I'll pick CR. Since it's given us moles, we don't need the grams per mole. So I'm going to say 0.50 moles of CR. I need moles of CR down here, and moles of H3, 4 up here. That's the 2 reactions. And it's 2-to-2. So if you're afraid to take a guess from what you're looking at, this is how much we need for H3PO4. This is how much we have for H3PO4. So is H3PO4 limiting or excess? It's excess because we have more than we need. So this is excess. And this is limit. PCR limit. That's the question. Let's just find the limiting reactant. Yeah, this involves grams. Exercise 72. They give you the unbalanced equation. I'll give you the balanced equation though. I need at least 2 of those, 6 of those. I think that does it. So there's the balanced equation. I'll give you balanced equations to work with. Lithium and nitrogen. So that's what we're given to react. Okay, so which one is the limiting? What's your first step? Pick one. I'm just going to go with lithium. I have 1.50 grams of lithium. Lithium is grams per mole. One mole of lithium is 6.94 moles of lithium. So this is the molar ratio. 6 moles of lithium to 1 mole into 1 to 6. All right. And the grams of N2 is 14.01 times 2, so 28.02. So moles of N2 1 mole of N2 is 28.02 grams of N2. So let's see how much we need. So 1.50 times 28.02 divided by 6.94 divided by 6 gave me 1.01. That's how much N2 we need. Here's how much we have. So is that excess or limiting? We need this much. We have this much. It's excess. We have more than we need. So this is excess. And that means this one is limiting. Humidity's killing me. Of course, I brought a Red Bull, not water. Red Bull's not helping. All right. More of these. This is kind of an easy one. You're given the theoretical yield, and you're given what he actually got. A student got 25 grams of product, but theoretically should have given 81. 25 is actual, 81 is theoretical. That was simple. Okay, let's do 64. And if I outline what's there, here's the reaction. It's balanced. Got 0.53 grams of CO2. All right, this one is the long walk, because we're not even told what's excess or limiting. What do you call this? This is the actual yield of CO2. All right. Since this is just decomposition, there's not two reactants, so we're just going to use the calcium carbonate. You know what, let's not do this. This gets me to the review of stuff that I didn't put on chapter 1, on test 1. So I'll come up with examples for that, these type of things to put on D2L. This is so I think I have actually done all of these. I just didn't put them on test 1. So this might feel like a review. Okay. How many grams of NaCl? So you might imagine you're going to need grams per mole. This is 0.250 liters. The 5.30, the M means moles per liter. So I would go ahead, when you see that capital M, go ahead and go 5.30 moles per liter. The M, I just wish no one ever invented that because there's no reason for it, that we can't just write this instead of M. But that gives you a clue of what it represents. And then of course I would tell you to go one more step and go 5.30 moles of NaCl in 1 liter of NaCl solution. If you do that first, it frames you in a lot on how to solve one of these. So the 5.30 M really represents 5.30 moles of NaCl in 1 liter of an NaCl solution. I would go ahead and translate it into that. Let's see. Liters. How many grams of NaCl? One of those, one of those. Is 2.99. I want to do this in my head. 22.99. Here, 22.99. That's 35.45 grams per mole. But of course, we're going to use 58.44 grams of NaCl on mole NaCl. So we've got this that we're going to use. We've got this that we're going to use. I think we have everything we need. So start this with 250 liters. Liters. This is liters of NaCl solution. Because it says liters, realize that means NaCl solution. You've got NaCl solution here and NaCl solution here. Liters of that. You've got liters of NaCl solution up here, so I need liters NaCl solution down here. So that means this is the next thing I'm going to use. There's no solution on these. That's NaCl and NaCl. Liters of NaCl solution, liters of NaCl solution. So 1 liter of NaCl solution and 5 moles of NaCl. Okay, now it means moles of NaCl on the bottom. One mole of NaCl. 8.4 grams of NaCl. That'll end us on grams of NaCl, which is what we're asked for. Point 250 times 5.30 times 58.44. That's 3 significant figures. That's exact. 3 significant figures. That's exact. 4. So I need 3. So it's going to be. Let's answer to that. 'This is to check your learning. For that example. Done exactly the same way. We're going to need, it mentions grams of CaCl. Calcium 40.08. Before you do anything, just to frame yourself in, 2.00 M means moles per liter. More specifically, moles of CaCl2 to 1 liter CaCl2 solution. Now, add solution to the liter. Since this is in liters, I need this in liters. You could just move the decimal here and say I have 0.250 liters. If I wanted to do it a little more formally, I would just go and then I would put that next hold off on that. This is. So I'm going to use this, I'm going to use that. I'm going to start with the milliliters. So the formal way to go from milliliters to liters is, so I'll do that. But that's the same thing as moving the decimal this way 3 times. And it cancels the milliliters and puts you in liters. So liters is up here. Maybe I should say milliliters of CaCl2 solution. And then just to be formal, CaCl2 solution. And now I'm going to use this, milliliters to liters. So I use this here. And now I've got milliliters of, liters of CaCl2 solution on top. So I need liters of CaCl2 solution on the bottom, which means I'm using this. That gets me to moles of CaCl2. One mole of CaCl2 is 11098. I'll just trust their answer with 5.55 grams. She's what they have here. Acetic acid and vinegar instead of water for the solvent. The concentration of acetic acid and vinegar is this. volume of that solution contains and I just looked down there. It's so we do need the grams per mole, but it didn't calculate it. Okay, we're gonna need that. 0.839 down, go 0.839 moles per liter, and then go in this case, the acetic acid solution is vinegar, so the wording might be a little confusing. But to calculate this, where do we start? We start with grams, 75.6 grams. Let's put some grams of acetic acid down here. So we're using this 60.05 grams of acetic acid to 1. That puts moles of acetic acid next. Here. We have moles of acetic acid here, so 0.839. And on top is the 1 liter so what volume of the solution? Liters. That'll do it. So for a problem like this, that's how you calculate it. If you're asked for milliliters, you're just going to have to convert the last step, liters to milliliters. .6 divided by 60.05 divided by 0.839. .50 acetic acid solution, aka vinegar. I'm dying. It is humid in here, right? I'm not getting sick again. The only one moving around is why I'm sweating. Anybody else sweating in here? It's just me. Better not be getting sick. Just got over it. To check your learning is worded a little more simply. This. But it's done exactly the same way. I'm more likely to word something like this for this type of problem. PBR solution. So potassium K is BR is 79, 90. Why does that not seem right? All right, fine. This, take it to 1.50 moles per liter, which is 1.50 moles of KBr to 1 liter KBr solution. We're going to use that. We're going to use this, grams per mole for KBr. So more formally that. So 66.0 grams is what we're given. That means grams of KBr on the bottom. Grams of KBr to moles of KBr. 1 mole of KBr is 119.00 grams. And then moles of KBr, moles of KBr. Moles of KBr on the bottom, 1.50 moles of KBr and 1. So what volume of this solution has 66 grams in it? 66 divided by 119 divided by 1.50. Three significant figures. That's what my calculator says. That's 3 significant figures. The 7 rounds to 9, so this becomes 0.370. Liters of KBr. Okay, this is the dilution formula. I bet you remember this, but I didn't put it on a test, so I'm going to do some of these. The dilution formula, more generally, this is concentration, volume, concentration, volume. Similarity. But I'm going to use, instead of C, I'm going to go, because we're going to stick with molarity and not the other, like percent solution and all those other concentrations.
fit it in there.
So you have this many liters of this concentrated solution. You dilute it with pure solvent. What is the new concentration? And the key to these is always just being able to identify what is M1 and M2. So there's an M1, this V1. So the ones are this. You start with this, and then the new solution that you dilute to is number 2, a new molarity and a new volume. So in this case, M1 is 5.00, V1 is 0.850, M1 is what we're looking for, and the new volume is 1.80. If you can identify that much, it's a very simple calculation. Can you see that these are what these are? So if I was doing it, I would go, I'm solving for the new M, so I need M1, V1, over V2, no, yeah, V2, Z2. M1 is 5.00, V1 is 0.850, V2 is 1.80, and what's that support? Divided by 1.80. One thing to check is since you're diluting this value for M2, this value for M2 should be lower than M1. If you're diluting it, it should be a lower number. And since you're adding pure solvent, so here's your starting volume, your ending volume should be larger than your starting volume. So this helps as a double check to make sure you didn't miss something. You guys good with that? So some molarity calculations and some dilutions. I've got a couple more here. Let's get this one. Let's do table 2.0. All right, can you tell what M1, V1, and M2, V2 is? That's the whole key to this, and if you could do that, the rest is very simple. Notice the wording here, can be prepared from 11 milliliters of 0.45 molar solution. So if you're going from one place to another place, the first place is 1 and the second place is 2. So if you're going from here, are those 1 or 2? Those are the ones. 11 milliliters. It's got parentheses here, and it says liters. It converts that to liters. As long as you keep it in milliliters here and here, you actually don't have to put it in liters. I know that seems weird because this is moles per liter, but this is one case where the units, as long as you stay consistent, it won't matter whether you convert it or not. So I'm going to use 11 milliliters. And just to remind myself, I'm coming out in milliliters here, if I'm going to use milliliters here. 0.45. So here you're just solving for this. M1, V1, and then we divide by M2. M1 times V1, M2, and now come out in milliliters because I kept that as milliliters. 0.45 times 11 divided by 0.12. Calculator says 41.25, but really we're just working with 2 significant figures here. So 41 milliliters. Oh, what's this last one? Yeah, I'll do this one. Again, these come down to figuring out what's M1 and what's V1 and N2 and V2. Is required. Look at the wording. So what volume of this, of M, 1.59 molar KOH solution is required to make? So, is this the 1 or the 2? The 2. Very good. So, the volume is 5.00 liters, molarity is 0.100. That M is 1.59. In this case, we divide by M1, so and M2 is 0.100. V2 is 5.00. M1 is 1.59. 1 times 5 divided by 1.59. 3 significant figures. added liters, so we come out in liters. And that's right. So for just 0.314 liters, add pure solvent all the way up to 5 liters. And that takes you from 1.59 molarity down to 1 molarity, 0.1 molarity. All right, we gotta stop there. I need a little better dehumidifier. That's killing me. So I'll include that in this series. Going forward, this we made it all the way through. I'll get stuff on D2L, I promise.